Hi guys, I felt really bad about not finishing up the notes from yesterday. It's Friday. So I thought I would just really quickly go through a couple of those problems that we didn't finish up. And that way, if you have questions over the weekend, you'll be able to kind of look that up and see what you were doing. So let's see here. I'm going to close my face. Maybe. Or not. Back to tab. There we go. Okay. We were finishing up here on number 9. So we've got a rectangular piece of sheet metal is 10 by 10. Squares of side lengths X are cut from the corners. And so I'm going to grab a shape here really quick. Let's grab a square. So I've got a square. Well, it says a rectangular piece of sheet metal, but it's a 10 by 10, so it's a square. So we've got a square piece of sheet metal. There are squares cut from each of the corners. So something like this. We're assuming that all the squares are equal, probably so that this way they could fold the box up. Oh yeah, there we go, next sentence, so that it is folded to make a box. The volume of the box is modeled by this equation, and it gives us the equation, so we don't have to come up with our own, yay. And we want to know what size pieces could come from the box if the volume is going to be 25. So basically they're telling us right off the bat here, our volume is 25, so 25 equals, and then we have our 4x to the third minus 40x squared plus 100x. So really what we can do is we can subtract that 25 over to the other side. So we can have 0 equals, we'll have all of this, and then we'll just do our minus 25 at the end. So now we can take this over to Desmos.com and we can type it in and see what possible solutions would make the most sense. So let's do that. We'll go over to Desmos and we'll type in our 4, get to the right, x to the third, oops, not ampersand, x to the third minus 40x squared plus 100x minus that 25. So we can see we have 3 zeros on this graph. It makes sense. There's 3 possible solutions. So we can't really say, so if 6 is the biggest value here, 6.019, if I cut 6 out of the sides of that box, if I was to take this and put, the whole box, remember, is 10 tall, 10 wide. If we were to cut 6 out of each corner, well, that would make 6 and 6, that would make 12, and that's bigger than the side of the box. So that's not a possibility for us. The smaller one we have there, we have a side, so this one doesn't work. So then here 2.8 or 0.281, that would be itty bitty. That's like not even a quarter, just barely a quarter of an inch. And so that's going to be really, really small as well. And it's going to be too small to actually make anything out of the box. We're just saying the box is only a quarter of an inch tall. So that's going to be really, really short. So that's not going to work either. So that means this 3.7 must be our only possible solution. So I'm just going to type that in here. 3.7 is the only realistic solution. 6 is too big, and 0.28 is too small to work. Perfect. Okay, so then the next page, we've got another word problem here. It says a rectangular column of cement is to have a volume of 20.25 feet. So it's a rectangular column, so that's good. The base is going to be a square, even better. So we've got a square. Actually, let me undo that. I'm going to draw it with a marker. It's going to be easier. So we've got a rectangular column of cement. We're going to have a bottom that is a square. So something like this, all the sides are equal. The sides are, so the base is a square with sides 3 feet less than half the height of the column. So that means this base is going to be 3 feet less. So I'm going to subtract 3 from half the height. And that would be the same on both. So we'll do half the height minus 3. And the height would just be the height, whatever it is. So there's our picture that represents our solution here. So let's write an equation to represent the volume. Well, we know that volume is equal to length times width times height. We know our volume is supposed to be 20.25. It's going to equal the length, which is 1/2. I'm going to write that as 0.5 h minus 3. And then I'm going to have another one that's 0.5 h minus 3. And then the height would just be h. We're going to multiply that out, box it all in, make it all work. So if I was to do this with the box, right? So I have, oops, let me draw it in the rest of the box. Box it all out. You guys probably can do this faster than me at this point, but 0.5 h minus 3. This one's also going to be 0.5 h minus 3. Make this work a little better. There we go. So if I was to multiply this out, that's going to give me, let's do this in purple. That's going to give me 0.25 h squared for my first box. I'm just going to write that as 0.25 because I ran out of space. This one would give me minus 1.5 h, that's J. This one's going to also give me minus 1.5, oops, make that purple, minus 1.5 h. And then the last one would be plus 9. So we know we have here 0.25 h squared. Negative 1.5 plus negative 1.5, that's just a nice easy, minus 3 h plus 9. I've still got to multiply that all with this h over here. So really I'm going to save myself a second here and just distribute my h right off the bat. So that'll make that to the third power. And then here again, I'm going to take that 20.25 and I'm going to just subtract that over. Obviously in this problem, I have a lot of decimals and I don't like decimals. They're fine, but it's probably going to be a whole lot easier to do all of the factoring, everything that we're going to need. Well, actually, we're going to use Desmos, so I guess I don't have to. I could just leave that as my equation. I would have multiplied out because I don't like decimals. I can see it's all 25 is a quarter. This is, again, a quarter, so I could just multiply by 4, and that would make, so if you wanted to do that, I could do everything times 4, and that would just make that 1, h to the third. I'm going to just grab these. This 3 times 4 would give me 12, 9 times 4 would give me 36, and 20.25, so 20 times 4 is 80, and then I'd have 81. So there would be another way to write your equation so that you don't have to deal with decimals. So just by multiplying everything, I guess I don't really need to multiply it all, oops, by 4, so that I can more easily type that in. But again, it doesn't really matter. So using Desmos, find the dimensions of the column. So 1h squared to the third. Oops, I keep hitting the wrong button here. So I'm going to clear this out. I've got 1h to the third. Oh, except I can't use h. I have to change it to an x. 1x to the third minus 12x squared plus 36x minus 81. So we can see here, height of our column, that's easy. It's just going to be 9. So height is going to be 9, which means that our length and our width are going to be the same. It's going to be half the height minus 3. So I have to do half of 9 minus 3, which would make that half of 9 is 4.5. 4.5 minus 3 would be 1.5. So our height is 9, our length would equal 1.5, and our width then would also equal 1.5. Boom, there you go. The last one, and this is the one, and I know there's questions on your homework about this too, is figuring out the turning points. So we're going to graph these in Desmos and answer these questions. So how many x-intercepts do you expect to see? So we should probably expect to see actually 2 x-intercepts. And then what are they? So let's graph it. X minus 3 squared plus 2. So we can see x minus 3 squared, squared, and then x plus 2. Probably should reset this. There we go. We got 1, 2 x-intercepts because that's where they cross the x. That's where they're touching the x-axis. We can see that we have one of them that's going to bounce on there, and that is because it's bouncing. Okay, I was just checking something out. It's bouncing off that x-axis, and that's because on here we have an x to the third, a power, or x minus 3 squared. So that extra exponent is what makes it turn at the x-axis. So we expected to see, or we saw 2 x-intercepts. I won't write that for the whole thing. It's just, I figured, why not? Or I guess we could say we see 2 x-intercepts. They are x equals 3 and x equals negative 2, which comes right off of these, highlighter here, right off of these 2 values here. So if we just set those equal to 0, we can find our x-intercepts really quickly. Then how many turning points does the graph have? So what we mean by turning points is not like where you reach your maximum or minimum, but where does it bounce off the x-axis. That's what we mean by the turning point. Are any of the x-intercepts a turning point? If so, which one? So again, we're just really driving home this idea that when you have a double x, when you have a double, like a squared term, that's when you're going to see that bounce. So where does it bounce off the x-axis? Well, it bounces off the x-axis at 3, right there. And so we can see how many turning points does it have? It has 1 turning point. And so then the last part then is, are any of the x-intercepts a turning point? Yes. If so, which ones? It was our x equals 3, because that's the x squared term. Okay. When we come over here to this next one, we should expect a turning point at x equals 0 because of this. So I should have 1, 2 solutions again. And if I go in and graph that, x squared times x plus 4 to the third. So I'm going to do this as just x squared and x plus 4 to the third. And so sure enough, I've got a bounce at 0, and I've got an x-intercept at negative 4. So our x-intercepts, we have x equals negative 4 and x equals 0. We again have 1 turning point, and it is our x-intercept, because again, that's the x squared term. Okay, so then when we look at this one, how many x-intercepts should we expect? We should expect 2 x-intercepts again. We should see them at negative 5 and 1, because that would be our solutions for these 2 equations. X plus 5 and x minus 3. So this will be x plus 5 and x minus 3. Double check that. Oops, sorry, no, x minus 1. There we go. So x plus 5, there's our x equals 5, x minus 1. Now notice on this one, it doesn't bounce off of the x-axis here. It doesn't hit the x-axis and then bounce back up, and that's because this is an x to the third, not an x squared. So how many turning points does the graph have? On this, there are none. And then we don't have to answer the second one, or the last one. On the last one then, we should see we have 1, 2, 3 intercepts. And that is because, and we should see them at x equals 0, we should see them at x equals 6, and we should see them at x equals negative 3. Okay, so I'm just solving these 3 equations. Let's double check that and make sure. X minus 6 squared, x minus 6 squared, and then it was x plus 3 and not cubed. There we go. So sure enough, negative 3, 0, and 6. We have 1 bounce, and that's because that's where it's been squared. So 1 turning point, and x equals 6, because that's where the term that was squared. So then just generalizing your findings regarding the number of x-intercepts, number of turning points, and when a turning point happens at an x-intercept. So when we think about this, we can say our x-intercepts, so just throughout the whole notes, we should have as many x-intercepts as there are exponents. Sometimes the intercepts are repeated, and sometimes they are imaginary. The turning points that we see are, so the turning points, and I'm going to put in parentheses, bounce off the x-axis, those turning points happen in the x value or group is squared. Okay, so just trying to really drive that idea home. That's what we're looking at there. Okay, so that was the rest of the notes. I do feel bad that we were close, but we didn't quite finish that in class. So I just wanted to make sure that you guys got a chance to see all of that. So, alrighty, I will see you on Monday.